Welcome to lecture 20. So last time we looked at the spring mass system. We looked at case 1a, the free undamped motion. Today we're going to be making our way through the two other cases, so free damped motion, which also has three subcases associated with it, and then driven motion. Okay, so we'll go through these, and then I think in the next lecture, lecture 21, we'll go through an example. Both hand-derived and also using MATLAB or Octave. But let's look at case number 2 here. So free damped motion. So free motion indicates that this right-hand side f of t equals 0, and damped indicates that this constant beta is non-zero. Okay. So if you recall, this was the second-order linear ODE with constant coefficients that governs the spring mass system. M here was the mass of the thing on the end of the spring. Beta was the damping constant. K was the spring constant, and M, B, and K are all positive. Okay. X was the extension of the system past the spring's equilibrium position, the equilibrium position when it has the mass attached to it. Dx by dt is the velocity of the system, or the mass on the end of the spring, and the second derivative of x with respect to t is the acceleration. F of t on the right hand side was some external force. So in the case of free damped motion, f of t is 0 and beta is non-zero. Okay, so we get a second order homogeneous ODE. Okay, and I can write this again. I want to divide through by the mass because I don't really want to carry that mass around. So if I divide through by the mass, I get beta over the mass plus k over the mass. Okay, and if you recall last time, k over the mass, k over m, I called omega squared. And now, so that was omega squared equals km. So now I'm defining this thing 2 times lambda to equal beta divided by the mass. Okay, so lambda has to be greater than 0. 2 times lambda equals beta over the mass. Why do I have the 2? Well, you'll see when we solve this system that the 2 just makes the mathematics a little bit easier. Okay. So if we wanted to solve the system, we first write down the auxiliary equation for this ODE. And so we're going to get m squared plus 2 times lambda times m plus omega squared equals 0. Okay. Well, I forgot the equals 0 on the auxiliary equation here, but imagine that's equals 0 here, and we can solve this equation for the two roots, m1 and m2, right? So if we do that, just using the quadratic formula, you can see that the 2 actually disappears, so there's no divide by 2 here, of course. So this is why we use 2 lambda, because we just get something that looks a little bit nicer. So we get minus lambda plus or minus the square root of lambda squared minus omega squared. Okay. And so the general solution to this second order linear ODE with constant coefficient is going to depend on the sign of lambda squared minus omega squared. So the sign of this stuff underneath the square root. Okay, so this is why we're going to have 3 subcases. So in the first case, this lambda squared minus omega squared is going to be greater than 0. So this stuff underneath the square root is greater than 0. We're going to get real roots, right? We're going to get 2 distinct real roots to this second order linear homogeneous ODE with constant coefficients. Okay, so we call this case something called the overdamped case. Okay, and we say it's overdamped because the damping coefficient beta is large compared to the spring constant k. Okay, so beta is up hidden in this lambda thing here. So this you can think of as the damping, something to do with damping. So the damping is larger than the spring constant. Okay, so we call this overdamped. So the words do matter here, overdamped, and we'll find underdamped and critically damped. So when lambda squared minus omega squared is greater than 0, we say it's overdamped. The general solution then in this case, again, I see we get two unique real roots, 2 distinct real roots. And so the general solution is x of t, the extension of the spring, in time equals some constant c1 times the exponential of the first root, m1 times t, plus c2 times the exponential of the second root, m2 times t. Now both the roots are negative, okay? And the reason for that is lambda is going to be larger than lambda squared minus omega squared, right? Because if I have something called lambda squared and I subtract something that's positive from it, well, this has to be smaller than just lambda itself. Okay, so maybe you could pause the video here and just take a moment to think about why lambda, we know that lambda has got to be greater than lambda squared minus omega squared. Okay. So that means that if we look at our two roots here, m1 and m2, lambda is greater than the square root of lambda squared minus omega squared. So both of these things have to be negative. Okay. So again, if you need to pause the video here and just think about why m1 and m2 have to be negative, that's fine. Maybe you should do that. If you think about it for too long though, just maybe send me an email and we can discuss it further. But okay, both our roots are negative, so that's good, because what that means for us is that x of t goes to 0 as t goes to infinity. If you look at the solution here, as t gets larger and larger and larger, if m1 and m2 are negative, then we get exponential of some negative larger and larger and larger number. Okay, and the exponential of, as the exponential goes towards negative infinity, the exponential of that goes to 0, right? So the motion, the x of t, the extension of the spring goes to 0 as t goes to infinity. Okay, and this is good because we know that this is what happens in real life. If you have a spring and mass system, you pull the spring down and you let it go, you know that it oscillates and then it slows down, slows down, slows down until eventually it stops moving and it just sits in the equilibrium position x equals 0. So, well, this solution is following what we know happens in real life, so, well, that's positive, that's good. We can find the motion is damped and eventually ceases, but we can find the maximum displacement of the spring mass system by taking a derivative equal to 0. So, remember from your first year calculus, if you want to find a maxima or a minima of a function, you take the derivative of that function and find out where it is equal to 0. Okay, so let's do that with our system. The derivative of x with respect to t, well, we basically just have an exponential up here, so the derivative of the exponential of m1 times t is just going to be m1 times the exponential of m1t. And similarly for the second exponential term. Okay. So I can simplify this system. I can write this system like so. I can pull out a common factor of e to the m1t. Okay, well that pulls out this term here, so I just get c1 times m1, plus c2 times m2 times exponential of m2 minus m1 times t. So, well, I can pull out that common factor there. If you want to get, you could put that factor back in. If you multiply e to the m1t times this second term here, you should be able to see that we get this original term back. So there's just a little bit of algebra there. This exponential term we've pulled out here, this is never 0, okay, apart from when t goes to infinity, so we don't care about the infinite case. But this derivative of x with respect to t is equal to 0 when this bracketed term is equal to 0. Okay. Okay. So we don't know exactly what time that's going to be, but we know that that can only happen in only one location. This equation has at most one local maxima or minima for positive time. Okay. And so the reason that is C1 and C2 are constants, M1 and M2 are negative here. In fact, the only t dependence of this in this whole equation is in this exponential. So there is only, you could rearrange this equation for t. You're only ever going to get one value of t that will satisfy this equation equal to 0. Okay. So the motion is not oscillatory because there is only one local maxima or minima. Okay. If there were multiple maxima or minima, then you could say this is going to be oscillatory motion. But because this is the overdamped case, there is too much damping to get oscillatory motion. We either get no local extrema, so no minima or maxima, so we just release the spring and it just damps away to the equilibrium position, or we get a single local extrema, so where we get maybe some, well, x is increasing here, so this is the spring moving down, and then it moves back up, back to the equilibrium position with no oscillatory motion. And similarly for the case where the spring is initially moving upwards, and we change direction here, we start moving down to the equilibrium position. But there's only one minima or maxima in the overdamped case, okay, where lambda squared minus omega squared is greater than 0. Okay, so let's look at subcase. I mean, this is really unrealistic for a spring mass system, I suppose, unless you really specifically designed it in that way. For example, in a car shock absorber, maybe this would be an attractive thing to have, where it's not, the car's not bouncing up and down the road all the time on your springs. You just get damped to your car's equilibrium position. But okay, what about subcase 2 though? This is when lambda squared minus omega squared equals 0 exactly. So you get one repeated root here. Okay, this is what we call the system being critically damped, because if we slightly decrease the damping force, we get oscillatory motion. If we slightly increase it, then we get an overdamped system. Okay, so here lambda squared minus omega squared equals 0, so we get repeated roots. The square root term here is 0, square root term here is 0, so m1 equals negative lambda, m2 equals negative lambda. We have a repeated root. Okay, and we know from our studies of second order linear homogeneous ODEs with constant coefficients that if you have a repeated root, the general solution to that case is the exponential of that root, so negative lambda times time, multiplied by the constant c1 plus c2 times time. Okay, so this is from earlier in the course. Okay, so this is the general solution for the critically damped case. We can ask the same question as we did before, as well, basically, where does x prime equal to 0? Or in fact, firstly, let's see what happens to this general solution in the long time limit, because okay, we've got an exponential here, which as t goes to infinity, this is going to 0. But we also have a c2 times time thing here, which as t goes to infinity, this is going to infinity. So the question is, what happens to the behavior of the system as t goes to infinity? So we can use L'Hopital's rule to examine that behavior. So we have the limit as t goes to infinity of c1 plus c2 divided by e to the lambda t. So we've just taken this exponential on the denominator. By L'Hopital's rule, we know that this limit is equal to the derivative of the stuff on top, or let's say the limit of the derivative of the stuff on top divided by the limit of the derivative of the stuff on the bottom. So if the derivative of the stuff on the top, well, c1 is 0, c2 times t is just going to be c2, e to the lambda t is going to be lambda e to the lambda t. So we're looking at the limit as t goes to infinity of c2 over this exponential, which of course is 0, right? Because this exponential is going to infinity, so constant divided by infinity is 0. So thankfully, in this case, the critically damped case, the motion is damped and eventually ceases, or it goes back to the equilibrium position. Okay, let's take the derivative of this time to see where we get maxima and minima. Okay, well, if this is a, well, we have to have a product rule thing here, right? We have a exponential of minus lambda t times c2 times t, so we have a product rule we have to account for here. But if you take the derivative of this thing, then you get c2 minus lambda c1 minus lambda c2 times t, all multiplied by e to the minus lambda t. Okay, so this derivative equals 0 when t is equal to this number. If you rearrange this equation equal to 0, c2 minus lambda c1 divided by lambda c2. So all these things are constants, lambda, c1 and c2. So again, there is at most one critical point, and the motion is really graphically similar to case 1, the overdamped case. Okay, so if this thing, lambda squared minus omega squared equals 0, we have the critically damped case, and our system behaves like so. But let's then look at the final subcase 3. We have lambda squared minus omega squared is less than 0. So in this case, well, recall that if this is less than 0, we have some imaginary term in here, right? Because we have the square root of some negative number here. So we know we're going to get complex conjugate roots here. So we call this case underdamped because the damping coefficient is small compared to the spring constant. So here lambda squared is small compared to the spring constant, which is hidden in omega squared. Okay, so we get complex conjugate roots, negative lambda plus or minus the imaginary number times the square root of omega squared minus lambda squared. So these are the roots of the auxiliary equation. We know that the general solution to this case is equal to e to the, well, you can solve this, right? E to the minus lambda times time. So this is the real part of the solution, right? Minus lambda. Multiplied by c1 cosine of t times the square root of this thing. So this is the imaginary part of the solution. Plus c2 times sine of t times the imaginary part of the solution. And again, using that trigonometric identity from the last class, I can write this as the amplitude of the motion multiplied by e to the minus lambda t times sine of t times that imaginary part of these roots plus this phase angle phi. So this is very similar to case 1, in fact, where we had simple harmonic motion. But now, in case 1, basically lambda was 0. So if lambda is 0, in fact, this simplifies to simple harmonic motion. So we have an amplitude and a phase angle. Again, we can find the amplitude simply by looking at, well, this should be c1 squared plus c2 squared. And the phase angle phi you can find using one of 3 formulae here, okay? And the right one to use, we have to, well, depends on the situation. So we'll solve a system like this in the next lecture. Okay. But case 2, free damp motion, so the case where the function on the right hand side has 3 subcases associated with it. But all 3 you should know how to solve now, because we have solved quite a few second order constant coefficient homogeneous equations. Okay. So let's just look at this solution one more time before we move on to case 3. So notice that the sine function here is always between -1 and 1. Okay, this sine function is always bounded below by -1 and above by 1. So we know that the solution x of t is going to be between negative a e to the minus lambda t and positive a e to the minus lambda t, okay, because sine is always between -1 and +1. The period of this motion is going to be 2 pi divided by the square root of omega squared minus lambda squared. Okay, so that's what we call the period, or the periodicity. And so the solution varies between minus amplitude times e to the minus lambda t and amplitude times e to the minus lambda t, with a quasi-period or period of 2 pi over omega squared minus lambda squared. If you look in the long time limit, well, the limit of this motion is going to be going to 0 because, well, the sine just oscillates between positive and -1. The exponential, as t goes to infinity, that goes to 0, of course. So the motion is damped and eventually ceases here. And in this case, in fact, we're going to get oscillatory solutions, in fact damped oscillatory solutions, right? Because sine is just oscillating between -1 and 1, and the exponential is just damping out these oscillations. So in fact the solution to case 2, sub case 3, is we get some oscillatory solution with multiple minima and maxima until we eventually reach the equilibrium state, equilibrium position. So this is really going to be x equals 0 here. So this solution, in fact, what we were calling the underdamped case, this is probably like most spring mass systems that you've seen. You pull the spring down, the spring oscillates around a bit, and eventually comes to a steady stop, the equilibrium state. Okay. And then finally we can look at case 3, which is driven or forced motion. So this is the case where the right hand side is non-zero. Okay, so we have some external force on the system. I can divide through by mass, just like we have done before. So we get beta over mass, k over mass, and now also this f of t over mass. We rename everything in the same way. We call beta over m equal to 2 lambda. We call omega squared, we call k over mass omega squared. And now we're just calling this function lowercase f of t divided by mass. We're going to just call that uppercase f of t. Okay. So to solve the non-homogeneous linear second order ODE with constant coefficients, so that's all this is, right? This is just adding a non-zero right hand side. So it's just made the system non-homogeneous. We can solve this using the method of undetermined coefficients or the variation of parameters, right? So as an example, we can consider the case where the system is underdamped, so lambda squared minus omega squared is less than 0. So this is where we get oscillatory solutions. And let's add an external force of some constant f0 times cosine of gamma t. F naught and gamma are positive constants. The solution to this non-homogeneous ODE is x of t equals the complementary solution xc plus a particular solution xp, right? So xc, the complementary solution, this is the solution to the associated homogeneous problem. So imagine we're basically, to find xc, we're solving this system with the right hand side equals 0. And now we just did that, and we showed that that was equal to the amplitude times this exponential times this sine, okay? And then if we then use the method of undetermined coefficients on this system, so here we have a cosine, so we try a test solution or a particular solution of some number a1 times cosine plus a2 times sine, okay? And so we'd solve this in exactly the same way that we did for solving any second order non-homogeneous constant coefficient linear ODE. But again, we just need to be careful that the frequency of the forcing function, be careful if the frequency of the forcing function, so this cosine gamma of t here, equals the complementary solution frequency. Okay, so basically, well, you may like to go back over your notes as to what happens if that happens. Okay, so we get our solution x of t equals the complementary solution plus a particular solution, and for this particular case we were looking at, these are our complementary and particular solutions. Okay, we could actually write this particular solution in the same form as the complementary solution. So we could write this as f naught times sine of gamma t plus capital theta, where these two constants would depend on the specific system you're looking at. So the first term, x of c, the complementary solution, represents the damped oscillations, because this term approaches zero as time gets large. So we say it's the transient part, or the transient solution. Okay, but the second term, x of p, this is just a sine function, or you could say it's the sum of a cosine and a sine. Okay, and those things are not damped. Oops, there are no exponential damping here. There's no damping here at all. So these things just oscillate forever. So we say that this is the steady state part of the solution, or the steady part of the solution. Okay, so we've now presented our three cases, and so in the next class I'm going to solve an example, well, on the slides, and then also using Octave and MATLAB. So tune in next time for that. I'll see you there.